In this video, we are going to find all prime numbers p and q such that p cubed plus q cubed plus 1 is equal to p squared times q squared. Before we move on, don't forget to give a like, subscribe to my channel, and turn on post notifications. To solve this equation for prime numbers p and q, I'm going to divide the problem into two cases. The first case is that p and q are equal. Then from this we can say that p cubed plus p cubed, even this q becomes p, and same for this q. And so 2p cubed plus 1 equals p to the power 4. Now from this, we can see that these two terms are multiples of p. Then from this we know that the number at the middle, 1, also has to be a multiple of p. But this cannot happen. So there is no solution for this case. So we move on to the second case, which is that p is not equal to q. Now since this equation is symmetric about p and q, that means if I switch the order or location of p and q, the equation is still the same. So I can assume that p is larger than q. Of course, you can add before that, which is p is not equal to q. So under this assumption, we can say that by symmetry, p is the larger prime number. At this point, we can use a similar trick like the first case, which is that p cubed and the term at the right, p squared, q squared, are both multiples of p squared. So that means the terms in the middle, q cubed plus 1, adding them all together will also make it a multiple of p squared. So I can say that p squared divides this difference, which means p squared divides q cubed plus 1. But now p squared will also divide q plus 1 times q squared minus q plus 1. This is because we can factorize q cubed plus 1. And since p is a prime number, we can divide this into 3 further subcases. One is that p divides q plus 1, and at the same time p divides q squared minus q plus 1. That's the first subcase. Also, it's also possible that p squared divides q plus 1, and at the same time p does not divide q squared minus q plus 1. That's our second subcase, and our third subcase will be p squared divides q squared minus q plus 1, but p does not divide the other term in the product, which is q plus 1. So altogether, we have 3 subcases, and we know that these are the only subcases we will have because p is a prime, and we cannot further decompose p squared into product of some smaller numbers. So let's do this case by case. For the first case, we know that both q plus 1 and q squared minus q plus 1 are multiples of p. So I'm going to do some algebra on these two expressions. So firstly, for the first divisibility, I'll rewrite that as P divides Q squared plus Q, which is possible because Q squared plus Q is simply a multiple of Q plus 1. It's just multiplying it by Q. Then I can add these two expressions, and it's still a multiple of P. Actually, I should not do the plus, but I should do minus instead. Sorry for the mistake. Which means P divides 2Q minus 1. Now it's a much smaller expression because the degree is reduced. Now at the same time, going back to P divides Q plus 1 again, I have also P divides 2Q plus 2. So now I can take a difference again. And we know P divides 3. But since P is a prime, we know that P must equal to 3. And now then we can even solve for the value of Q. Which is that then 27 plus Q cubed plus 1 is equal to 4Q squared. And so Q cubed minus 4Q squared plus 28 is equal to 0. I don't even have to solve for this cubic because simply by looking at the parity of each term, these two terms are even. And the right is even. So that means Q cubed is even. And that implies Q is an even number. And since Q is a prime, Q must be 2. And indeed, Q equals 2 is a solution to one of the solutions to this cubic equation. So from this subcase, we know that the only pair of solution that it generates is P equals 3 and Q equals 2. So that's the first subcase. Now for the second subcase, because P squared divides Q plus 1, from this, we can say that P squared must be less than or equal to Q plus 1. And we have assumed that P is the larger prime over Q, so it's even smaller than P plus 1. Now from this, it's actually sufficient to say that it's impossible because P squared is never larger than or equal to P plus 1 when P is at least 2, because we have assumed that P is a prime number. So no solution for this case. Whereas for the third subcase, the argument is similar, which is that from the fact that P squared divides Q squared minus Q plus 1, we can say P squared is less than or equal to Q squared minus Q plus 1. But this is clearly less than Q squared because Q is a prime and it's at least 2. And of course, we have assumed that P is the larger prime, so Q squared is less than P squared. Again, a contradiction. So altogether, we have only one solution pair, which is that P equals to 3 and Q equals to 2. And under this solution, both sides will be equal to 36. So it's a valid solution. Please feel free to share your ideas in the comments. Thank you for watching. See you next time.